Welcome back to Cs231N, Lecture 13. Today we're going to talk about generative models. Last time we were talking about self-supervised learning, which is this really interesting paradigm where we want to somehow learn structure directly from data with no supervision, with no labels. And the typical the typical formulation of self-supervised learning that we talked about a bunch of examples last time is you have your big data set with no labels. Ideally, it's just images. This is great. You can get a lot of images. You're going to feed these through some kind of encoder that's going to extract a feature representation from your images, then go through some decoder that will predict something from that feature representation. And the whole trick in self-supervised learning is coming up with some kind of pretext task that you can train this whole system on without requiring any kind of human annotation or human labels. So we talked about things like rotation, different kinds of tasks that we can use as pretexts for these self-supervised, to formulate these self-supervised learning objectives. And then typically, this is usually a two-stage procedure where first you're going to go and learn this self-supervised encoder-decoder on your self-supervised task on all the data that you can find. And then after that, you're going to throw away the decoder and then slot in some new, maybe possibly tiny, fully connected network, and actually train this thing maybe end-to-end, or maybe just learn the fully connected network at the end, on some small labeled task. And the idea here is that via self-supervised learning, this pretext task you can train on lots and lots of data, millions, hundreds of millions, billions of samples where we don't have access to high-quality human labels. And in the process of self-supervised learning, it's going to learn something about the general structure of images or of data. And then you can transfer that knowledge to downstream tasks where you have small amounts of human labels. So then the typical setup you should keep in your mind that we want to work towards in self-supervised learning is that you're going to train on like a billion unlabeled images that we're getting from the internet somewhere. And then we're going to transfer those features to tasks where we're willing to sit down and label maybe tens, hundreds, maybe thousands of examples for particular tasks that we really care about. But we want those tasks to be improved by this generic knowledge that we've learned through this self-supervised pretext task. And we talked about a couple different kinds of pretext tasks last time, including rotation, rearrangement, reconstruction. All of these are basically having this sense of that you're making some geometric perturbation, geometric disturbance to the input pixels, and then you're asking the model to somehow recover from that perturbation. So in the case of rotation, maybe you rotate the image and you ask the model to predict how much it was rotated. In the sense of rearrangement or solving jigsaw puzzles, you're going to cut the image up into patches and ask the model to try to predict what was the relative arrangement of those patches in the original image. Or in reconstruction, maybe you're going to delete some parts of the input image and then ask the model to fill them in as some kind of in-painting or reconstruction task. And these are fairly successful. We also talked last time about a different formulation of self-supervised learning called contrastive learning, which has been very successful. And here I was told that you ran out of time a little bit to cover a couple of these later methods, so I wanted to just go over those really quickly at the beginning of today's lecture instead. The idea of contrastive learning is you're going to get pairs that are similar and pairs that are dissimilar. And you want to pull the similar pairs together and push the dissimilar pairs apart. And the way that you usually do this in the context of self-supervised learning is you're going to start with your input images. And again, these are unlabeled images. You don't have labels for them. And now for each input image, you're going to apply two random transformations. So in the case of the cat, we sort of took one crop around the cat's face, another crop around the backside of the cat, and around the monkey, we sort of took one around the monkey's face and also dropped it to black and white, and et cetera, et cetera. So basically, for each one of your input images, you're going to apply two, or possibly more than two, but two is a nice minimal subset, two random perturbations to your input image. Now you're going to feed all of those randomly perturbed versions of your input data to some kind of feature extractor, which could be a VIT, could be a CNN, any kind of neural network that can input an image and output a feature representation. Then you want to apply this notion of contrastive. So for each of the two augmentations that came from the cat, we want those two feature vectors to be the same. So we color them green. So basically, you basically compute this big n squared similarity matrix, where I guess it's 2n, open paren, 2n, closed paren squared. So then it's 4n squared. If you have n images, you put two perturbations on each. So we have a giant, 2n by 2n matrix for all these perturbed images, all these perturbed, augmented samples that we got. And now, basically, we want to pull together the two augmented samples, the two augmentations that came from the original image, and for every pair of augmentations that came from different original images, we want to push them apart. So you basically run through this feature, run all of these things through your feature extractor, compute this giant 4n squared matrix of all of your scalar similarities between those feature vectors, and then pull together the ones that are similar, push apart the ones that ought to be different. And that's the basic idea of contrastive learning. And one paper that really pulled all this together a couple years ago was called SimClear, that applied this very successfully to self-supervised representation learning on images. And that's the one I think you walked through last time. But one kind of problem with the SimClear setup is that it requires a fairly large batch size to actually get good convergence, because it's sort of too easy of a problem for the network. If there aren't that many samples, it's sort of too easy to pick out the two cat ones that looked similar. So to make the problem hard enough for the network to give it good enough learning signal, you tend to need quite a large batch size in order to get this model to converge to good features. And then once you do that, you need to rope in all the ideas around large-scale distributed training that we talked about a couple of lectures ago, which is totally feasible. It totally works. But you might ask, is there some way you can get away without that? And so that leads to a couple of approaches that I don't want to go into too much detail. I actually don't want to walk through these and tell you exactly how they work. I just want to make you aware of their existence and give you the general flavor of what they're trying to achieve. So in this MoCo, or momentum contrast approach to self-supervised learning, the setup is very similar to what we just saw in SimClear. You're taking data, you're getting augmented pairs, you run them through a feature encoder, you want to pull together the ones that are similar, push apart the ones that are dissimilar. But the thing that differs is that we want to get away with not having to have a gigantic batch size at every iteration. So to do that, they keep a queue of negatives. They keep a queue of samples from previous iterations of training. And then at every training iteration, I've got my X query is my current new batch of data, and I have this queue, X0, X1, X2 key, which are previous batches of data that I've seen on previous iterations of training. Now, my current batch of data, I'm going to run through my encoder network the same as I always did, and compute the contrastive loss the same way that we did with SimClear. And then this larger queue, these like previous history of batches, we're going to run through something different, the momentum encoder, and then still get feature representations and compute the same kind of similarity that we did through the SimClear thing. But the problem is that we don't want to backpropagate into the momentum encoder because it has too much data. It has too big of a batch. We can't afford to fit that in GPU memory. So we want to not have to backpropagate through that part. So instead, so that means that we cannot update this momentum encoder, the second encoder, via gradient descent. Instead, we're going to do something kind of wacky. What we're going to do is have this momentum encoder have its own set of weights. We're going to learn them not via gradient descent. Instead, what we're going to do is have the momentum encoder be a exponential moving average of the weights of the normal encoder. So the normal encoder, we're going to learn via gradient descent. Everything is normal. We'll forward prop, we'll back prop, we'll get gradients. We'll make a gradient update step on the typical encoder. That's the normal thing. But then after we do that, the momentum encoder, we're going to decay the encoder weights. We're going to decay the current momentum encoder weights by like 0.99, and then add in 1% of the encoder weights. So then the momentum encoder, we have this other update rule where it's this lagging, trailing, exponential moving average of the encoder weights. And I don't have a great intuition or explanation for why this exactly makes sense, but there's very strong empirical evidence that this works. So that's kind of the state of things. But it's nice because it means that you can now get away with learning these self-supervised representations without having to have this gigantic, massive batch of negatives at every iteration. And this was fairly successful. There were a bunch of follow-up papers that pushed this direction. Another one that you should be aware of is called Dino. Again, the idea is very similar. It uses this similar sort of momentum encoder, this like dual normal encoder that's learned via gradient descent, and a momentum encoder, just as in MoCo. But the loss is a little bit different. Instead of using softmax, they use some kind of KL divergence loss. And the reason I'm mentioning this one is because you should be aware of the existence of Dino v2, even if we don't talk about exactly what it does. Because Dino v2 is a really strong a really strong model for self-supervised features that's used quite a lot in practice these days. So what they basically did is took this recipe from Dino v1, which was kind of similar to MoCo, has a lot of ideas from SimClear as well, but a lot of unique details in their approach as well. But the big difference in Dino v2 is that they scaled up the training data quite a lot. So a lot of these previous self-supervised approaches had been trained on the ImageNet dataset, which was 1 million images. And Dino v2 was able to successfully scale up this approach to a much larger training set of about 142 million images. So, in deep learning, we like bigger networks, we like bigger data, we like more GPUs, we like more flops, we like all of those things. And Dino V2 was able to find a recipe for self-supervised learning that successfully scaled up to this much larger data set, gives very strong self-supervised features. And this tends to be used quite a lot in practice today if you want to pick up features and then fine-tune them or supervise them for some of your own downstream tasks. So again, I don't want to walk through all the details of how this works. I don't expect you to know, but I want you to know that it exists in case you want to pick it up and use it for some of your own projects in the future. So that's basically all I had to say about self-supervised learning. Any questions about that before we move on to the meat of today's lecture? Okay, guess not. So today, the main topic is generative models. This is really cool. This is an area of deep learning that basically went from not working at all 10 years ago to like really, really working in the last couple of years. And this has given rise to things like language models. These can be viewed as generative models, as we'll see. All kind of image generation models, all kinds of video generation models. These really went from just absolutely not working at all when I was in grad school. Like you would look at these samples and peer into them and they just look like low resolution, complete blurry garbage, but somehow you could view some promise in them. And I'm glad that people kept pushing on that and pushed through the blurry garbage and scaled it up over the past decade, because now a lot of these techniques really do work. And that's very exciting. So this is an area of deep learning that basically didn't work at all with the first time we taught this class, and that's really cool that it now does. But that said, like a lot of the fundamental ideas around generative modeling actually have remained the same. The ideas about how you think about data, what are approaches for modeling them, a lot of those mathematical fundamentals actually have not changed that much in the past decade. But what changed is more compute, more stable training recipes, bigger data sets, distributed training, and the ability to scale all this up into more useful tasks, I think, was really what drove the progress over the past decade. There were some algorithmic tweaks, and especially we'll see that next lecture when we talk about diffusion models. But first, before we talk about generative modeling, I wanted to step back a little bit and talk about supervised versus unsupervised learning, right? Because there's a couple of different tasks that we try to approach in deep learning, and they can sometimes be sliced along a couple of different orthogonal axes. So I wanted to talk about those a little bit, just so we get our terminology and our nomenclature clear. So supervised learning is what we've mostly been doing all semester, except for last lecture. In supervised learning, we have a data set of pairs x and y. And the goal is to learn some function that maps from the input data x to the target or label y. And we've seen a lot of examples of this kind of approach so far. Something like image classification. Our input x is an image, the output y is going to be a label. Or image captioning. The input x is going to be an image, the output y is going to be some piece of text describing what we see in that image. Object detection. Input is an image, output is a set of boxes and category labels describing the objects that appear in the image. Or segmentation. Maybe you assign a label to every pixel in the input image. And these are supervised learning problems because the task you're trying to solve, the thing you want to predict, is exactly what you have in your data set. And all you need to do in some sense is learn a function that mimics that x to y mapping on your training data set and then generalizes that mapping to new samples beyond your training data set. Now, unsupervised learning is something a bit more fishy and mysterious and hard to describe. But the idea of unsupervised learning, or sometimes self-supervised learning, is that you don't have any labels. You just have data. You just have samples X. You just have images. And you want to learn some kind of structure from that data. There's no particular task you're necessarily targeting. You're just trying to uncover good representations, good structure in all of that data. Why? So that you can, as we talked about in self-supervised learning, often so you can apply it to downstream tasks later on. But the task itself in unsupervised learning is often somewhat unspecified. Some examples of this are k-means clustering, where maybe we're trying to identify clusters in the data, which is some kind of structure that we can examine from the raw pixels that even though we didn't have labels for. Or dimensionality reduction, PCA, where we're trying to uncover some lower dimensional subspace or lower dimensional manifold that explains the structure of our data. And again, this is something we're trying to discover from the data itself. We don't have annotations of what this ought to be. Or density estimation. Maybe we're trying to fit a probability distribution to the data. We're trying to understand what is the probabilistic function that gave rise to the data samples that we're seeing. And again, we don't have explicit labels for this or an explicit training set for this. So this is some kind of hidden or latent structure that we're trying to uncover through the process of training. So this supervised-unsupervised dichotomy is something that you always should keep in mind. And you can do unsupervised learning, which is not probabilistic or not generative necessarily. Something like clustering, something like PCA, often they have probabilistic interpretations, but these are examples of unsupervised learning that don't necessarily have a generative or probabilistic interpretation or don't have to be thought of as such. So I often like to think about the supervised-unsupervised dichotomy as kind of one spectrum along which methods or systems can lie. A separate spectrum along which we can classify systems or tasks is that of generative versus discriminative models. And these are inherently probabilistic. And when we talk about generative or discriminative models, we're always imagining some kind of probabilistic structure in our data that we're trying to uncover or learn from. And the difference is exactly what is the probabilistic relationship between the variables that we're trying to model. So in discriminative models, so typically we have some y and some x. And usually we think of the x as something large, high dimensional, usually an image in our case. And the y is some kind of label or description or auxiliary information. And so that would be like your text, like your caption, like a category label, something like that. And when you talk about a discriminative model, we're trying to learn a probability distribution of y given x. So we're trying to learn a distribution over labels, conditioned on our input image x. And to really appreciate, what's going on probabilistically, you need to remember one very important feature of probability distributions, and that's that they are normalized, right? When you talk about a probability distribution, or more generally a density function, P of X is basically a function that applies, that assigns a non-zero number, to every possible input X, with the very important normalization constraint. That if you integrate over the entire space of all possible x's, it integrates to 1, right? And this normalization constraint really gives rise to the power of probabilistic models in some sense, because the normalization constraint means that all of your x's need to compete for probability mass. There's a fixed unit amount of probability mass, and choosing a probability distribution or density function basically amounts to apportioning out that fixed amount of probability mass and smearing it across all possible values of x that could exist. And all of those x's are in competition because there's only a fixed unit amount of mass to go around. So if you want to push up the probability of one x, necessarily the probabilities of or densities of other x's have to go down. So then in these different formulations of probabilistic models, basically what's changing is what are the variables that are competing for probability mass. And that means that even though the symbols that we write on the page look very similar, the different competitions among what is competing for probability mass, induces very different structure that the model is trying to learn or uncover. So in the case of a discriminative model, we're learning a probabilistic model of y conditioned on x, which means that for every x, our model is predicting a probability distribution over all possible labels. So if our labels are discrete and categorical, like cat, dog, then that means we have a fixed amount of probability 0 to 1, and cat and dog must sum to 1. And we have a separate probability distribution over the labels for every input x. And crucially, notice here that there is no competition among images for probability mass. Because every image is inducing its own distribution over the label space, there's no kind of competition for mass across the different images. The only things that are competing for mass are the different labels for each image. And that's very important when you think about discriminative modeling. And one interesting other facet of discriminative modeling is that they have no real way to reject unreasonable inputs. So once we've fixed our label space of, say, cat and dog in this example, if we feed in something that's not a cat or a dog at all, like a monkey or a piece of abstract art, the system has no flexibility. It has no freedom to say this is unreasonable. It's forced to output a distribution over the fixed vocabulary that we assigned at the beginning. So that's maybe could be seen as a shortcoming, but it's just important to understand what exactly is happening under the hood when you think about modeling different kinds of data probabilistically. Now, a generative model is something very different. Now, instead, what we're doing in a generative model is learning a distribution P of X. We want to learn a distribution over all possible images, X. And now this is very interesting. This means that all possible images that could ever exist in the universe are all now competing with each other for probability mass. And this is now really a hard question that requires, it sounds kind of simple on its face, but this requires you to confront some very deep and philosophical problems about the world. Right? Because now all images are competing for probability mass. And you're forced, in order to model that, you're forced to answer questions. You're like, should an image of a 3-legged dog, how should that get probability mass in relationship to an image of a 3-armed monkey? probably the three-legged dog should get more probability mass because that's, you can have that happen by a dog losing a leg. But how are you going to get a three-armed monkey? I don't know. That seems much more rare. Unless you're modeling sci-fi images or something like this. So once you're in this regime of all possible images competing for probability mass, now your model really needs to think very carefully about the kinds of structure that can exist in the data. And it becomes a much, much harder problem to solve. And another interesting thing here is that now with a generative model, the model now does have the capacity to basically say, no, this is not a reasonable image. This is not a reasonable input. And the way that it can do that is by assigning, low or even zero probability mass to any one image that it gets. So maybe in our generative model, maybe we only want it to recognize, be a generative model of zoo animals. And if we want to have a generative model of zoo animals, then, if we feed in an image of abstract art, it should have zero probability mass. So now we have a mechanism for rejecting or saying that this type of image is not within the scope of what we care about. And now a conditional generative model is even more interesting. So this is where we're learning a conditional distribution over images, X, conditioned on some label signal Y. And now this means that for every possible label, maybe we're now inducing a competition among all possible images. So in this case, if Y is, say, a categorical label of cat and dog, now, for each possible categorical label, cat and dog, the model is separately inducing a competition among all possible images. So now, in the top distribution, maybe this is the probability of all these images conditioned on the cat label. So then obviously the cat image should be high. Maybe the monkey and the dog image should be somewhat higher because they're still mammals at least, but the abstract art should be very low, maybe even zero. And then, a different distribution among images if we're conditioning on the dog label. And this gets even more interesting if you imagine that your conditioning signal Y is something much richer than a single categorical label. That conditioning signal Y might have been a text description. It might have been a whole paragraph of written text. It might have been another image plus a piece of text. So now once you talk about modeling these very rich output spaces X, conditioned on very rich input spaces Y, now you're actually asking the model to solve a very complicated and quite ill-defined problem that requires very deep reasoning about the objects involved. So that's why I think that generative modeling is such an interesting topic, because it looks kind of similar. It looks kind of simple. All we did was flop the X and the Y. How hard could it be? But all of a sudden, it required us to think really hard about what's going on in the visual world. And what's also interesting is that we wrote down discriminative generative models and conditional generative models as three separate categories of things. But actually, they're all related. And they're related through Bayes' rule, which is, one of the most amazing relationships in probability. And in particular, it says that, if we have access to a discriminative model, P, Y of X, and an unconditional generative model, P of X, as well as some prior distribution over our labels Y, we can compose those to build a conditional generative model, P of Y given X. Or in general, you can always rearrange Bayes' rule in some way so that if you have any two of these, you can always get a third one, which is pretty cool. So in practice, like in theory, you can in principle build a conditional generative model out of the other two components. Although in practice, this is not really how you do it. You tend to sort of learn conditional generative models, from scratch on their own. Although, as we'll talk about in diffusion, you do end up sometimes learning conditional and unconditional models jointly, for some reasons. But this is nice to keep in mind that there's a very deep relationship across these different flavors of probabilistic models. So then you might be wondering, okay, what can we do with these different flavors of probabilistic models? With discriminative models, this one shouldn't require a lot of creativity. We've seen a lot of these examples so far this quarter. So with discriminative models, after you train them, you can assign labels to data. You could also do feature learning, right? In the case of, say, supervised learning on ImageNet, we've seen that in the process of trying to predict categorical labels of images, those models tend to learn useful feature representations in the middle that can be transferred to downstream things. So this is so you tend to use discriminative models for just directly predicting the Ys that you care about, or for learning feature representations that are induced in the process of trying to predict those Ys. Generative models, actually these unconditional generative models, I think are actually kind of useless in general. But what they kind of let you do is maybe detect outliers, look at images and say, do they really have low probability mass? Are they unreasonable images? You can sort of use them for feature learning without data, without labels. So hope that in the process of trying to fit an unconditional distribution P of X, the model maybe learns some useful feature representations. Although in general, these have not been super successful for self-supervised learning. And typically the contrastive methods that we've talked about in the previous lecture have in practice been much more successful for self-supervised learning as compared to unconditional density estimation. Or, in principle, you could use this unconditional generative model to sample and produce new samples X. But I think this is actually kind of useless, because it gives you no control over what is being sampled, right? If you have an unconditional generative model of images, then you can sample from it to get a new image, but you have no control over what's in that image. So I think that's actually, it's mathematically interesting to think about how to build such models, but I don't think they have as much practical significance. And conditional generative models are where I think actually things are the most useful and the most interesting. And these are the kinds of generative models that get trained and used in practice by far the most. So you can, in principle, use them to assign labels while rejecting outliers, right? You could say, if I have a piece of data X, then look at the P of X given Y over all of my possible Ys, and then, I could reject if that's too low among all the possible Ys. So in principle, you could use conditional generative models to do some kind of classification while also maintaining the ability to reject outliers. Although I don't think that's really used too much in practice. What's really useful for conditional generative models, and what is used in practice all the time everywhere, is sampling to generate new data from labels, where you actually get to control what is generated, right? Because if your Y is now maybe a piece of text, you can write down, I want to see a cat wearing a hot dog flavored t-shirt on the moon or whatever. And then your favorite generative model of images will now generate you a brand new image X conditioned on that label Y. So this is where I think all the juice is, where all the magic is, where all the excitement is. Although somewhat confusingly in the literature, whenever you see the term generative model, they kind of mush up between unconditional and conditional generative modeling. And a lot of the papers that you read will even sometimes drop the conditioning signal Y because it makes the math look cleaner, it makes the equations look cleaner. But I don't think unconditional generative modeling is super useful. It's almost always conditional generative modeling that you really want to do in most cases. So just be aware that if you read papers, see equations, hear people talk, when they talk about generative modeling, they're probably the one they care about training more are these conditional generative models, even if the math even if the equations or notation doesn't reflect that.
So, for unconditional generative model, what are the inputs and outputs?
So I didn't really tell you that. And I was sneaky there because how you parameterize that actually depends a lot. There's a lot of different formulations for all of these things. And what exactly are going to be the inputs and the outputs of the network are going to vary quite a lot depending on the formulation. So we're going to talk about a whole taxonomy of those in a couple slides. Okay. So, why generative models? The main reason you want to build generative models is whenever there's some ambiguity in the task you're trying to model. Right? So the beauty of a probabilistic model, P of X given Y, is that it's probabilistic. There might be a whole space of possible outputs X conditioned on that input label Y. So whenever there's not, sometimes there's just a deterministic mapping, right? I look at an image, I want to ask how many cats are in the image. There's just 3 cats. There's just one answer. But in a lot of cases, it's more subtle. If I ask for a picture of a dog wearing a hot dog hat, there's a lot of different images that could exist based on that query. There's uncertainty in the output. And that's exactly what generative models are trying to model. They model a whole distribution of outputs conditioned on their input signal. So anytime that there's ambiguity in the kind of output that you want the model to produce, conditioned on the input, that's where you want to turn to a generative model. We'll see a couple examples of where this has gotten used a lot in the last couple of years. So one example is language modeling. Someone asked about ChatGPT a moment ago. So in language modeling, what you're often trying to do is predict output text X from input text Y. Sorry, the X's and Y's ended up flipped in an awkward way on this example. So here's an example from ChatGPT. The input is write me a short rhyming poem about generative models. And wow, it actually works. This is crazy. This didn't work at all when we first taught this class. I'm not going to read it. That will be embarrassing. You can read it yourself. Now this is a conditional generative model. You could imagine there's a lot of different possible rhyming poems about generative models that one might write. And we had to pick one of them. And the beauty of a generative model is that it, in principle, models that whole distribution over possible outputs conditioned on that input. Or text to image. Make me an image showing a person teaching a class on generative models in front of a whiteboard. You're kind of looking at one example through your eyes. ChatGPT gave you a different example, right? There's a whole different space of possible images that might match this input text. And a generative model allows you to model that whole space and sample from that space depending on what you want. Or image to video, input an image, what happens next? This was me holding my AirPods over a cardboard box. Maybe I'm going to drop it. Maybe I'm going to move my hand. Maybe I'm going to move my hand and the AirPods will morph into different kinds of AirPods. There's all kinds of things that could happen. A generative model in principle lets you kind of model and sample from these possible futures. So this is sort of why we want to care about generative modeling. Anytime there's ambiguity in the output, that's when you want to try to turn to a generative model to solve it. And someone asked about what are the inputs and outputs. It turns out this is a huge field. And this is surprisingly one field of deep learning that is quite mathematical, because it requires, thinking about what are different ways to model probability distributions. How can we write down loss functions that cause the right things to happen? So this is one area where when you read papers, there may be a lot of math. There may be a lot of equations. And you actually might need to think through those equations pretty carefully to understand what's going on. So this is one subfield that tends to have more math and more equations, which I think is kind of fun, kind of interesting. So there's this whole taxonomy of different kinds of generative models that people build. So on the one hand, you can imagine one part of the family tree are what we call explicit density methods. These are ones where the model actually does, the whole thing is we're trying to model P of X or P of X given Y. And with these explicit density methods, you can actually compute, you can get that value out, P of X, for any sample X. And the counterpoint are implicit density methods. These are ones where you can't actually get that probability mass value. You can't actually get that density value P of X out from the model, but you can somehow sample from that probability distribution. So the difference here is that in an implicit model, right, you can't actually access the value of the density function, but you can sample from the underlying density function somehow. So the model has implicitly learned to model the density, even if you can't get the value out. And on the explicit density side, it's almost the opposite, where in many cases, even when you can get that explicit density value out, but then sampling tends to be more complicated sometimes with these explicit density methods. Not always, but sometimes. Right? And the reason why you might turn to implicit models is because in many cases, you may not actually care about knowing what exactly was the density value for any input. Maybe all you care about is generating samples and generating good samples, generating a good diversity of samples. So if the thing you really care about is sampling, then maybe you don't actually need to explicitly be able to see the value of the density for any input. And then things break down and cascade and get more fractal-like from here. So inside explicit density methods, there's ones where actually, yeah, you can really compute the real P of X that's being modeled. And autoregressive models are one example of that. Or another version of explicit density methods are ones where you can get a density value out, but it's not the real one. It's some kind of approximation to the true density of the data. And variational autoencoders are one example of an explicit but approximate generative method that we'll see. Now, on the other branch of the family tree, we can think about direct methods for implicit density. These are ones where maybe it requires a single network evaluation to just draw a sample from the underlying distribution that's being modeled. And a generative adversarial network is an example of a generative model in this part of the family tree. And the other part is, I don't know if it has a good name. I called it indirect, but this is a name I made up yesterday, so please feel free to correct me if there's a better term for this. But these indirect ones are ones where you can sample from the underlying density P of X that's being modeled, but it requires some kind of iterative procedure. There's no feed-forward function where you can input and get the sample directly out. There's some kind of iterative method that you need to run in order to draw a sample from the underlying density that's being modeled. And diffusion models are an example of this that we'll see next time. I told you a couple slides ago that people are sloppy with notation and drop the Y, and I did that explicitly on purpose on this slide so that someone would ask me that question, and you would always be attentive to that fact. So yes, exactly. Every time I've written P of X on this slide, and actually all the rest of the slides this lecture, I also have been lazy and dropped the Y, but you should always imagine an additional condition on Y in all of these P of X's that you see for the rest of the lecture. So thank you for asking that. So the question was is the indirect method, is it still, can you just treat that indirect iterative procedure as a black box and then treat that as a direct sampling method? In principle, yes, but in practice, no, because your samples kind of end up approximate. Depending on exactly the method, but with diffusion models, you kind of would need to take an infinite number of steps in order to draw a true sample. So instead we approximate that with a finite number of steps. And that's, true of other methods as well. Diffusion models are the most common for this today. But, some kind of Markov chain method or MCMC method in years past might have also had this property where there is an iterative procedure, but if you want to draw an exact sample from the distribution that's being modeled, you need an infinite number of steps to converge. So we always approximate that by taking a finite number of steps. Okay. And I was pretty proud of this taxonomy because it's very symmetric. There's, there's 4 leaves, there's 2 branches, and we're going to cover half the tree today and half the tree next time. So I thought that was a pretty nice breakdown. The question is, what's the difference between the approximate density and directly sampling from an implicit P of X? The difference is that even in an indirect but implicit method, there's no density value anywhere to be found. You can't compute one at all. But you can still iteratively sample in some way. With an approximate density method, you can still get a value out. Like you can actually get a density value out that's going to be some approximate or bound to the true P of X.